Hello everyone, this is Pulsar from Tencent, and today's session is about how Tencent applies Apache Pulsar to Apache InLong. Well, let me introduce myself a little. Well, I'm currently working in Tencent Big Data Group as a software engineer, and my job is mainly focused on the storage, which includes, of course, the message queue. And recently, the main part of my work is the incubation of Apache InLong along with my colleagues here. And besides from this, we also put much effort on the evolution of Pulsar. And some of the features, for instance, KOP, will be covered later in the discussion. And I'm also fascinated by the big data technology, Hadoop, Flink, and all that. Well, a lot of you may have not heard of Apache InLong before. In fact, the project was named as TubeMQ just 1 month ago. And the TubeMQ was developed by Tencent in the first place, and we donated the project to Apache in September 2019. And however, later on this year, we found out the overall system around TubeMQ might also be valuable for the users. So we decided to make the whole platform open source. Oh, this includes the data access from the all the way to the storage. So InLong can serve as a one-stop data stream platform that provides automatic, secure, distributed data publish and subscription capabilities. And the InLong now supplies over 60 trillions of messages generated per day inside Tencent. And among them, the Pulsar plays a very important role. As you can see from the picture, InLong supports a lot of famous applications like WeChat and the mobile version of Battlegrounds. So here's a simple picture to demonstrate some of the basic units or components in InLong. As we mentioned before, InLong serves as a one-stop data access platform. So where does the data comes from? Well, we mainly support two kinds of sources, which includes the log files of the user programs and also some of the database information such as the binlog and SQLs. And besides from this, we also provide the HTTP access, and users can decide whatever data they want to put in our system. And the data can be then absorbed by the ingestion level. Here, the agent plays an important role. We designed this component by the experience of some of the excellent software such as DataX or Flume, and we did some optimization on them. Okay, so the data can be delivered to the Converge module. Here we have the InLong bus. Bus can transform the data by the message protocols so that the message queues can identify them. Also, it can serve as a fault tolerance mechanism when some of the data are rejected by the message queue, such as tube. This part of data can be stored in bus local storage and can be used for further recovery. And it also provides some of the monitoring on the data access and reported stats to the manager above. Okay, so then the data comes to the most fundamental part of the system, the cache part. Know that we support three cans of cache method. First of all, is Pulsar. Of course, we'll explain why we choose Pulsar here. And for the users who used Kafka before, we will introduce them the KOP, which can help users to publish the Kafka messages to Pulsars without changing any code. And of course, we have TubeMQ here. So after we cache the messages in the cache level, the data can be consumed by the InLong sort, and it decides how the messages can be passed later. For instance, users can use different business IDs in the data. We use this different business ID to determine the table, which table they want their data to be stored. The sort can also split the messages into different columns using the specified splitter set by the users. Okay, so in the last level, the data can be used by online computing platforms such as Flink, and also the data can be simply just stored in the databases. Also, the users can use SDKs to consume messages directly. And there's some requirements for MQ. in long. And first of all, the MQ should be reliable, right? And the data we had in Tencent can be payments, user privacies, and players' stats, and no data loss or errors can be tolerated. Also, the amount of data can be massive. Such amount of data can put the message queue a heavy burden, and the message queue should manage them well under this great pressure. Well, at the end, the consumer latency should be as low as possible because some of the machine learning algorithm requires short consumption time. So before we choose the MQ for Apache, we did some tests from different perspective. Note that this test is performed under certain machines and it cannot be applied for other cases. Here we have three kinds of MQs, including Tube, Kafka, and Pulsar. And for latency, here we have here the Kafka has a little bit of latency, while Pulsar and Tube MQ performs pretty much the same. And this is the same for the TPS. However, we need to mention that the Pulsar is a little bit difficult to manage. The reason is that it has more components than TubeMQ for the fact that it uses Bookkeeper as storage and Bookkeeper to store the configurations. However, as we get more familiar with it, such problem will be alleviated. And TubeMQ simply put his data in his local broker's local files. Or for the filter consume function, we can see that the tube can support both filter and client side, while Pulsar and Kafka only support on the client side. And note, we can see that the TubeMQ doesn't have the replication for data, which is the main drawback when users want their system to be reliable. And the most brilliant feature we think in Pulsar is the auto recovery. This is done automatically without human interaction. We know that in Kafka, such operation often drives people crazy because you need to transfer the data to other brokers manually. And this could be a disaster. If the replicas and reduced to a certain amount, the Kafka topic cannot be used anymore. And also for the client languages, the TubeMQ supports C++ and Java, where the Kafka only have one official client support, which is Java. We know that you can find a lot of Kafka clients, but only Java client is maintained by Kafka. And here Pulsar has seven clients, which includes the Java, Go, and all that. So in the end, we choose TubeMQ because it performs well and it requires a lot of less resources to support those who can take the small risk of losing some of data, and Pulsar for those who want both high performance and high reliability. And here we're going to present a data stream on how we apply the Apache InLong and Apache Pulsar in certain cases. So for Tencent Ace, which is a big department mainly focused on the advertisement. So their data they want to use is the bin log in their databases. Among them is the information about the transactions they made, and they need the bin log as some kind of backup or maybe useful for some of the analysis work. So the data flow should be look like this. The data generated in bin log can be collected using agent. If we use the agent to collect bin log, the agent serves as a slave of the database, so it can read all the bin logs. The data can be then sent to the bot servers. Bot servers will receive all the data from different agent machines. Bots will then get them and transfer them to the messages, and then it sends messages to Pulsar cache. Note that the users can consume all of them in many ways, such as Flink or sort. And here sort can sort the messages to different tables in Hive. And the data can also goes to MySQL or a Elasticsearch for other scenarios. Well, here we mainly use 4 features in Pulsar. First of all, we know that the Pulsar has low latency and consumption. This is many of the because of the well-designed read-write mechanism to keep in Bookkeeper. Sorry, and also we also the key shared mode. We use different key for different advertisers or different consume logic. Possible make sure that the messages inside the same key can be consumed sequentially. Also, Tencent Ace have massive consumers for one topic, and Pulsar can manage them well. Last, we use the later queue to store those messages that cannot be consumed correctly. as indicators for future troubleshooting. There are another case that we apply in until know that in this case we mainly focus on how we turn in the Pulsar to support the case better. So here's the problem. We have something called the federated learning, and it means that normally we run our machine learning algorithm in local machines, and that's where we get the our training data and labels from. So what if we have a task that requires data coming from different parties? Because we always know that the more data we get, the more likely the accuracy will get better. So how to transport all the data from one party to another? As you can see from the picture, the PowerFL is a federated learning platform designed about upon Angel, which is a machine learning algorithm library. First of all, we have to choose the communication method, whether it's RPC or MQ. We know that for the remote process control is a network connection between one machine to another. It may works well, but what if there are multiple parties? Okay, so we choose Pulsar in the end because it separates the process into just producers and consumers. We also have some requirements here. Because first of all, because the QPS varies for different training tasks, some of them may require a lot more data when training, and there should not be data loss because we're delivering some gradients. And it should be fast because we're using Spark as the computing engine, and the training time is dependent on the transmission time. Last but not least, it should be secure because we're using data from different companies, and the data should not be attacked by third parties. Okay, so here's how we're gonna do this. Here, the cluster A have a training task produces data to its local A cluster, and then the geo replication replicates the data to be asynchronously. And we use different topic names to separate the data at different stages. And then the B training task can get its data from his cluster B. Here we can specify the parties by setting the parties parameter. Well, here we have some challenge because we're first of all we are using global zk. We know that in Pulsar we have global zk and local zk. We use the global zk to store some of the information about different clusters. So here we'll increase the difficulties when we deploy the system, because every time we need to add a node in the global zk for each party joined in the federated learning. Also, the topics will grow dramatically because we have so many stages during the training. Besides, the broker may be unstable sometimes because at different stages of training we have different QPS. If we have some errors during the process, the whole training work needs to be rerun. Okay, so how do we remove the global zk? First, we have to register the newly added cluster in our local cluster. This can be done by the Pulsar domain. And then we need to authorize the namespace to the other cluster. So by doing this, we don't need the global zookeeper anymore, because we have the information in our local zookeeper. Okay, so now we know that we cannot delete the topic directly when you open the geo-replication. So in order to delete all the topics that are stored before, we need to open the delete inactive option to let the Pulsar delete them for us. There are some requirements. First of all, there should not be active producer or consumers of this topic, and no subscription, sorry, and no messages that should be stored in this topic. And we set the frequency seconds to 3 hours for the Pulsar to delete them for us. And also, to solve the problem, QPS can be pretty high. We use the production throttle, and we use the we actually put a limitation on the message rate. Also, in this case, sometimes the topic can be available. After some research, we know that the topic uploading is too often. We know that in Pulsar, a namespace can be split into different bundles, and bundle is actually a hash circle. So when a topic is added, the hash value of the topic names is used to determine which broker should take care of it. So if there are a lot of topics in one bond range, the bundles need to split. So the clients are going to reconnect to the brokers. We set these parameters to reduce the possibility of this. First, we increase the broker max topics numbers and max topics for bundles, and also the max match rate for bundle split. Okay, and we also created enough bundles at the beginning of the namespace creation. So by doing this, the bundle split won't happen too often. Okay, so geo-replication can also be applied as a fault tolerance in InLong, and it works well when we have clusters in different regions. So if the cluster are separated in different cities, if the system are separated in different cities, we can build this kind of replication map between them. So if one request is from Beijing and needs the data from Shenzhen, and it won't go all the way to Shenzhen and only we only need to read them locally. Also, the clustering, if the clustering in Shenzhen goes down, the whole system will still work fine because we can find the data in other places. And we apply this kind of deployment in Tencent QQ mining world, and know that this would cost a lot of more resources because you have to build the clusters in different regions. Also, in some other cases, we can simply just build two clusters inside one region, and it requires less resources when doing so. And this works well when you have producers and consumers inside just one region, and it will cost more, but it will cost more time when the requests are from different areas. Okay, so from the last slides, we know that we can use geo-replication to achieve fault tolerance. But the problem is that we need to manually switch the cluster when cluster is unavailable. And there's a time gap between the process. And so the users need to wait before the cluster is available again. This may not be acceptable in some strict cases, and we come up with this strategy called failover producer. And in this modified producer, it contains two Pulsar producers. Also at one time, only one producer is active. We also have a monitor here to check the errors inside a time window of the producers. So if the active producer are not available anymore, it can switch to the failover producer immediately. Here, the consumers needs to subscribe to two clusters because it doesn't know which one is active now. So by doing this, we'll achieve the goal of auto disaster tolerance. So we also found some other problem while we are running in InLong. For instance, when we are facing too many business and users, there might be numerous topics inside one namespace. So we decide to develop some of the features called filter consumption to reduce the number of reduce the number of topics. And we did this by adding tags in post message. Know that we have two parts inside one post message, the metadata and the payload, and we add the user specific tags in the metadata, and the metadata is used for the storage of some other information about the message. Okay, so first the producer here can add tags in the messages, and then the consumers will subscribe to the topics, and it pass the tags that they want to consume to the broker itself. So that when the broker publish the messages to the consumers, will first look at the metadata and then get the tags in it. And if the consumer has one tag that matches one of the tags in this message, the broker will publish to it. So by doing this, we achieve the filter consumption and consumption, and we no longer need the huge amount of topics to support our users. Okay, so besides from of all this above, we also did some optimization on KOP Kafka on Pulsar. Well, I'm not going to go deep into this because one of my colleagues is sharing it in another talk. When we're deploying KLP in InLong, we found out that some problems like the rebooting of Pulsar of the KLP clusters gets slower and slower. Well, actually, this is because of the offset topic we build for KLP, and this topic is used for the storage of Kafka offset, and it contains more and more data, and so it has lowered the start of the KLP cluster. We overcome this by setting the max retention time and use the topic compact function to reduce the number of data stored in this topic. Okay, so also we are using POSA, the ledger ID, entry ID, batch index, all of them to represent the offset in a Kafka. So by doing this, we know that the offset is not continuous anymore. And also here we reduce the length of the ledger ID, entry ID to 20 bits and 32 bits. So when the ledger ID is larger than 20 bits, the whole KOP cluster won't be available again. We solved this problem by introducing the broker entry metadata. The details will be given by Zhang Dawei in another talk. And also we are facing with the frequent out of memory error. We did this by using the throttle method produced by the Pulsar itself. Okay, so this is all about today's session. We have discussed the structure of InLong and how we applied Pulsar to it while we're running it in Tencent. So if you have any questions, feel free to contact me. I'm sure you can get my email address from Pulsar. Thanks.